Hi, students. This is Mr. Halpern here. We're going to be learning a little bit about heat combustion and heat of combustion. Combustion really is just an exothermic reaction, meaning that it's releasing heat and it has a negative delta H. And this is really a reaction between a fuel and oxygen. Don't forget oxygen, to produce the products of carbon dioxide and water. This is one of the foundational reactions that we learn in chemistry, combustion, because a lot of chemistry and a lot of why we use chemistry is for making energy, which is a huge part of our lives, and it helps to really make the society and the way that we live a reality. So an example is the combustion of methane. Methane is one carbon, CH4, and methane is a gas. It is a gas because it has a really, really low boiling point, meaning that even at very low temperatures, it's still a gas. We have to put in some oxygen, as we said in the statement above, for a combustion reaction, and we get CO2 and H2O. We also get some energy coming out as a product. And again, this indicates that it's an exothermic reaction, meaning that heat is going to come out. If I had an endothermic reaction, well, then this would be on the other side. That would be an endothermic reaction because total or net, I would have to, add more energy. So before we get moving on, you might have thought, hey, this doesn't look like it's that balanced. I have one carbon on each side. I have four hydrogens. I have three oxygens. So how do we balance this? Well, if I balance the hydrogens by putting a 2 there, then I have four oxygens. How do I balance that? I put another 2 over here, and now it's a balanced equation. Don't think that ever is forgotten. Balancing equations, it's very important in chemistry. So the formula that we use to measure the amount of heat given off by a reaction is Q is equal to MC delta T. And Q really is delta H if we have constant temperature. I'm sorry, not constant temperature, constant pressure. We can assume that we have constant pressure for this. So really, I could also write this as equal to delta H. So when we think about our energy diagrams, when you think about the difference between the reactants and the products and the amount of potential energy, this is a way of measuring that, all right? So let's talk about what each of these mean here. The Q stands for heat energy. And this is the amount of heat that's either released or absorbed. Okay, and it's either a plus or a minus. If it's released, it's a minus, or if it's plus, it's absorbed, and that would be an exo or endothermic reaction, respectively. This is measured in joules, Joules, and it's abbreviated as J. So you'll see the letter J there. That helps to represent energy. M is the mass of the substance that's changing in temperature. And this is measured in grams, G. Next, we have C. Now, C is really important. We are multiplying these variables, Cm, C, delta T. Each of these are multiplied with each other. And C is really important. C is something called the specific heat capacity. If we're heating up a particular material, we want to know how much energy it takes to heat up that particular substance um, of a particular amount. We're going to say a gram by 1 degree. And it's a way of comparing substance to substance. Some substances have, 1 or 2 joules for every gram that is raised 1 degree. Some have 3 or even 4 joules that they require to take 1 gram of that substance and raise it 1 degree. The higher the specific heat, the more energy it takes to heat up that molecule. And that tells you a little bit about that molecule itself. It tells you that it probably has stronger bonds and intermolecular forces. Maybe it has hydrogen bonds, and those are maybe harder to break up. Okay, it's the amount of energy it takes to raise the temperature of 1 gram 1 degree. And so we measure this as, again, it's the amount of energy, so it's joules, J, divided by 1 gram times the delta C, which is 1 degree Celsius. So this is the unit. The last one is delta T, which is how much did that particular substance change in temperature? And we do this by calculating it with a formula here. And this is the formula. It is delta T equals final temperature minus initial temperature. All right. So sometimes we can write this out. Instead of writing delta T, we can put in place T final minus T initial. So we have some practice problems here below. So let's try one of these here. So if we have 0.564 grams of magnesium and it's heated from 34 degrees up to 56 degrees, how much energy was given off? Magnesium's specific heat capacity is 1.02 joules per gram per degree Celsius. Well, so we want to try to figure out how much heat's given off, meaning that it's probably exothermic if it's releasing heat. So we take Q, we set the mass in here, we put it as 0.564. We put the specific heat, 1.02, and we put delta T. So what's the change in temperature? 34 and 56, that would be 22 degrees. Okay, and we multiply this together, and let's get an answer. I believe we get 12.66 joules. Okay, that's 12.66 joules right there. There are other practice problems here, but I want you guys to practice them by going through them. I'm going to continue on here. Now, I want you to think about why do we, or how do we measure this? What is the way in which we can actually take a look at this particular, this calculation? And one way is to show you a picture that I put together right here. And this is a very simple calorimeter. Calorimeter is an instrument used to measure the heat of reactions. So you might be wondering, like, what kind of materials do we use to measure temperature? We use a thermometer. How do we contain some sort of fuel? Well, we have a sealed container. Um, just to take a look at this image here on the left. Let's all focus on the left-hand side for a sec. This is a basic setup for measuring a particular fuel that is uh, always really challenging to measure in terms of how much heat's given off. And you can imagine sitting next to a campfire. If I asked you, please tell me how much heat is given off by a log of wood, what would you do? It would be really challenging. First, it'd be very difficult to and dangerous to try to measure the temperature change, right? And then temperature change would be also really challenging to measure too, because a bonfire would be something maybe outside, and it would have this environment that would constantly lose all this energy. It would be very difficult to measure. And so a basic calorimeter like this is a very simple version of the actual calorimeters that they use to measure heat of combustion and heats of reaction. What we assume is that we light the particular uh, fuel on fire. This is the human torch, right? And it lights. And what we assume is that all of the energy that this human torch's hand gives off, if we put this particular container down close enough to the fire, we assume that all or most of the energy will go into heating up the water that's in here. And water is a great substance. First of all, it's very easy to get in a sink, so we can fill up a container. And we know a lot about water. We know the specific heat, right, which is C. What else do we know about it? We can determine its mass, and also we can determine the temperature change of water. We don't have to burn ourselves or worry about that. So what we assume is that all of the heat that's given off by the fuel source is equal to the energy that's absorbed by the water. And that's not really a perfect assumption, but we're going to go ahead and assume it anyway. It also gets lost here. Not all of it goes directly into the water. Some of it gets absorbed by the container or the thermometer itself. As you can feel the thermometer, maybe you pull it out and it feels warm. That means that it didn't go into the water only. It heated up the glass of the thermometer and the aluminum of the can. So it's not perfect. But what we assume is that these two equations are equal to each other. And again, if we assume that the heat energy that's released equals the absorbed energy in the water, ooh, that's messed up. That should say absorbed. Then we can do some calculations and we can use our basic understanding and measurements of water to determine something about an unknown fuel. I'll give you an example. Let's take a look at the human torch's hand example. Let's say we have 15 grams in this container right here, okay? And that water goes from 15 degrees to 37 degrees. How much heat did the human torch's hand give off then? What we can assume is if we assume that they're equal to each other and all the heat that was given off by the human torch was absorbed by the water, then we can use these numbers in here and calculate how much heat was given off. So the heat of the human torch, HT, we're going to assume is equal to the heat of the water, which is equal to the mass of the water, the specific heat of the water, and the delta T, the temperature change of the water. That's what we're going to assume. So let's solve this. We have a mass of 15 grams. I'm sorry. Yes, we have a mass of 15 grams. We have a specific heat of water, which is always 4.18. And we have a delta T of 1537, so we have total of 22 degrees in temperature change. What is that amount of energy? 15 times 4.18 times 22 equals 1,379.4 joules, or 1.38 kilojoules. Okay? All right. The last parts of this here is really a little bit more complex, and we're going to go into this in class. So no worries if you can't do the next parts. Feel free to give them a shot if you'd like, but that is a little bit more challenging for you. All right. Take care, and I will see you guys later.